Okay, I think we can start. So today's talk is given by Professor Padakandla from Tennessee at Knoxville. Arun did his PhD in University of Michigan. He is expert in information theory, multi-user, complicated stuff. But then he joined our center, and we worked together on privacy. And then when he went to Tennessee, he started working intensively on quantum information algorithms. And today, I understand, will be a general introduction. The next week will be more probably technical. Arun, please.
Okay, thank you. Thanks to it's really very nice to be giving this talk. It's also very nice to be hearing about this joint seminar series between CSOI, Purdue University, and Jagiellonian University, if I'm correct. You know, the pronunciation is slightly hard, but I read about I read about the Jagiellonian University and Jagiellonian, right?
Jagiellonian.
Yeah. Jagiellonian, yes, exactly, Jagiellonian. I read about it. It's a prestigious university, so I'm very happy to be giving this talk. Thanks to Wojtek for giving me this opportunity. And you know, this series has been kind of so organized so that the next few talks, I mean, before you get to know more about the research results, you can kind of get a feel for, you can get an introduction to quantum information. So Wojtek was suggesting that I give a talk giving you the basics of quantum information before. There will be some talks by Mohsen. There will be one talk by me on quantum research results in quantum. So this talk is an introduction to quantum information. So please feel free to ask questions. The idea is to kind of, you know, give you some basics of quantum information, quantum computation. And the goal is to kind of, you know, you should get excited at the end of this and you want to go and read more of quantum information. That's kind of the broad goal. So in this part, what I will do is I will talk about some foundations of quantum information, give you some basics. The goal is not to cover a lot, but the goal is to kind of get you some feel of quantum information, you know, how it's modeled, what kind of algorithms you can do, what do you mean by a quantum gate. These are basic things that I would like to kind of just communicate. Possibly, I mean, this talk is actually made for a little longer than an hour, so I won't go through the entire talk, but possibly what I will cover is the axioms of quantum mechanics and the quantum gates. And at the end of the talk, if you kind of get to know some basic power of the axioms and some basic quantum information processing, I would have, you know, achieved my goal. Yeah, I am a native English speaker. I mean, and you might be, you know, Polish. So I mean, you will be Polish. So I'll speak a little slow. So don't get impatient. Okay. So this talk is, the aim of this talk is to convey the ideas. Okay, quantum information is quite heavy in math. The tools are quite involved. You need to know operators, infinite dimensional spaces and stuff like that. My aim is not to kind of tell you all the rigor of the math, but to convey the ideas, the key ideas. You can always go and figure out the math, and even the math you can try to understand in its simplicity. Okay, so the goal is kind of ideas. Throughout, there will be one running thread throughout this talk. I will be comparing classical information bits and quantum information bits. So you can see the contrast and you can kind of understand, you know, what are the differences. And that's a good way to understand. And again, this talk is very pictorial. Don't get bogged down by the math. There is not much text on the slide and you don't have to read it. You can just kind of listen through the pictures and kind of listen to me and get everything. Okay. So the power of quantum algorithms, right? So, you know, you would have heard people say, you know, the Shor's algorithm can factor integers much more efficiently and stuff like that. All of this power crucially relies on the unique behavior of quantum systems. So if tomorrow you have to either understand or design some powerful quantum algorithms, you need to have a good grasp of the behavior of quantum systems. How do quantum systems behave? You need to understand that very well. And the behavior of quantum systems is described through 4 axioms of quantum mechanics. Okay, so that is going to be the first topic of this talk. If you understand the 4 axioms, I mean, if you can kind of get a feel for these 4 axioms, you have achieved a lot, because it takes time to kind of grasp this. And what I'm trying to do is kind of do this in a kind of pictorial, kind of a cartoonish way, so that you get a feel for these axioms. And once you start reading it, it's much easier for you. That's kind of the broad goal of the first part of this talk. So axioms of quantum mechanics. Okay, so again, as I said, I will always contrast classical information and quantum information, so you kind of get a feel. Okay, so let's look at classical information or classical data. A bit lives in 0, 1, in the set 0, 1. So its state space is the set 0, 1. Okay, and a bit can be either 0 or it can be 1. So the question is, where does a qubit live? Axiom 1 answers this question. Okay, so the state space of a quantum system is an inner product space. And the most simple inner product space we know is R3. So I have given you a picture of R3 here. So, and a quantum system is described by a unit vector in H. That inner product space is denoted H. And I will tell you why it is denoted H just in the next slide. Okay, so just bear with me. So just as we say a bit takes values in 0, 1, and a bit takes a value 0 or a 1, very analogous statement is that the state of a quantum system is in a inner product space, the state space. So the state of a quantum system lives in inner product space, and a quantum system is described by a unit vector in the inner product space H. Okay, I'll give you an example. So very simple example. A quantum system can be described by this vector 1 by root 2, 1 by root 2. Okay. So this vector could be just the polarization of photon, or it could describe the polarization of a photon or the spin of an electron. So it could be 1 by root 2, 1 by root 2, or it could be 1 by root 2 minus 1 by root 2 and stuff like that. Okay. So a quantum system is described by a unit vector in an inner product space denoted H. So you might ask the question, why do I denote this inner product space as H, right? So general quantum theory is actually based on a Hilbert space. The state space of a general quantum system is a Hilbert space. What is a Hilbert space? So Hilbert space is a complete infinite dimensional inner product space. Okay, but we'll make life simple. Now let's not complicate it. We just have a Euclidean space with standard inner product. That is our Hilbert space. You can just think of RD. If you want to be sophisticated, you can think of CD. I mean, complex vector space to d-dimensional complex vector space. But if you're not comfortable with complex, like most people are, you can just think of the Euclidean space, d-dimensional Euclidean space, R power d. So that's our Hilbert. That's our state space. So just the set 0, 1, which was in the bit in the classical information, now has got translated into an inner product space. Now, what is a qubit, right? You may ask, what is a qubit? A qubit is just a 2-dimensional quantum system. In other words, a quantum system in a 2-dimensional Hilbert space or a 2-dimensional inner product space is a qubit. Okay, so 2-dimensional quantum state is a qubit. There are 2 special qubits. That is the ket 0. So this is this left bracket. This is denoted as ket 0. This is called ket 0, and this is called ket 1. Ket 0 is the vector 1, 0, and ket 1 is the vector 0, 1. Okay, but there is a caution here. In classical information, your bit can either take the value 0 or it can take the value 1. But a qubit can take any linear combination, any convex linear combination of ket0 and ket1, any complex linear combination of ket0 and ket1, so long as the vector has a unit norm. Okay, so this is a point I would like to emphasize. So I mentioned this here also. So a quantum system is described by a unit vector in the inner product space. Okay, so all of this is part of the first axiom. I'm kind of elaborating it and kind of explaining it to you so that it's easier for you to understand the rest of the presentation.
Arun, so you are assuming norm 2, of course, yes?
Yes, norm 2, yes.
Exactly.
Thank you. That's norm 2. My inner product space is endorse the norm 2 norm. Okay, so this, whatever I've illustrated, right? Again, I told you in the beginning, this talk is not like going to be rigorous. The goal is to convey the ideas. So this actually is not the right illustration because we are talking of C2, right? And here it looks like an R2 space, right? So the correct illustration is actually through what is called a block sphere. And that's an involved representation, so I'm not going into that. But for all practical purposes, you can think of this as just a two-dimensional vector. Okay, so that's a qubit. So the first difference we see clearly is that whereas bit can take either the value 0 or 1, a qubit can take any superposition state. So alpha and beta can be complex scalars so long as mod alpha squared plus mod beta squared is equal to 1. Okay, so the norm of the vector should be 1. And you might ask this question, and what does it mean to say, alpha ket 0 plus beta ket 1? I'm reading this as alpha ket 0 plus beta ket 1. What does it mean to say? And some people try to interpret this as the system is in state ket 0 with probability mod alpha squared and ket 1 with probability mod beta squared. Because you're tempted to do that because mod alpha squared plus mod beta squared is 1. You're tempted to do that, but it's not the right illustration. Okay, the right way to think of this is indeed a state by itself. Okay, so no probabilities there. Okay, I talked about the inner product, and Wojtek asked me a question about this, so let me clarify. So the inner product between the ket x and ket y is essentially y1 star x1 plus y2 star x2. So I denote the inner product by this bracket yx. This is denoted as bra. So the left angle is the bra and the right angle is the ket. So this is bra ket. Okay, so it's bracket yx. And mathematics usually conjugates the second argument, but physics conjugates the first argument. Okay, so there's always this difference, but it doesn't matter really. So we'll just take the physics notation. So even when mathematicians write books on quantum systems, they actually gulp the physics notation and they adopt the physics notation. So the inner product between x and y is y1 star x1 plus y2 star x2. So now this clearly induces the L2 norm that Wojtek was talking about. If you are in R2, you don't have to worry. You can just say y1 x1 plus y2 x2. Okay, now qubits are going to be our information carriers. Okay, so analogous to bits. So just like as we like kind of operate functions on bits, we are going to do something on qubits. So qubits are our information carriers. So I'm going to run this thread through and through. Remember that I told you that I'm going to always contrast classical and quantum, so you kind of get a feel. So classical world, look at the right side. Bit is an element in a finite set. Quantum, it's a unit vector in an inner product space. Classical world, our state space is a finite set. Quantum world, our state space is an inner product space, which is a Hilbert space. In the classical world, information we encode is in the bit x. In the quantum, the information we encode is in a vector, which is ket phi. In the classical world, x takes a value in 1 among 0 and 1, but in the quantum, it's a vector in a inner product space. So I'm saying this because you're seeing all of this for the first time. I see this every day, but I'm just trying to recollect so that you kind of keep in touch with what's going on. So unit norm, keep in mind the vector is unit norm. Inner product with finite, this is inner product, finite dimensional inner product space, FDIPS. I might use sometimes. It just means finite dimensional inner product space. Just think of R2. Okay, don't complicate it. Okay, so as I said, our universe is essentially the inner product space, right? So let's kind of get get acquainted with the objects in our universe. Okay, so let's kind of understand what are the tools in our universe. So the most important tool is the linear transformation. So, when you study linear algebra, the first thing you'll study is linear transformation. So the linear transformation plays a very important role throughout quantum theory. So if you're somebody who is comfortable with linear algebra, vector spaces, rank, nullity, Hermitian operators, Hermitian matrices, positive definite matrices, you should stop doing everything you're doing and start working on quantum information, because you're going to be considered very hot very soon. Anyway, so a very important transformation is a unitary transformation. What is a unitary transformation? Unitary transformation is simple. It just preserves inner products, or it just preserves the length of vectors. So think of a unitary transformation as just a rotation. Okay, so I've given you an example. Phi is just rotated through a unitary transformation to u phi, u ket phi. Okay, so unitary transformation is a linear transformation that preserves lengths. The next important, the second most important object in our universe is a projection operator. Okay, I'm giving you a nice example of a projection operator. So you take the ket phi. So ket phi is this vector. If you project it on this surface, then you get a projection, right? So pi is a projection, and you can write a matrix representation for this projection operator. It is just it projects on the first two bases. So this is a projection operator. So what is a projection operator? If you ask more, fundamentally, what is a projection operator? A projection operator is something that satisfies this relationship: pi squared is pi adjoint equal to pi. Okay, so it's an operator that when squared is itself. So it's like one. It's like one, and you should kind of keep that in your mind. Okay, so I have introduced unitary operator transformation. I have introduced a projection operator, and I'm going to start using all of this now. Okay, make a few observations about projections, which we will use later on. Okay, so suppose I take two projections. So the projection 1 projects on this blue surface at the bottom, and projection 2, pi 2, projects on the vertical axis at the top. So you can write the matrices for pi 1 and pi 2. Pi 1 is essentially this matrix, and pi 2 is the 0, 0, 1 matrix. And you observe that pi 1 plus pi 2 is the identity. Okay, and observe that when pi 1 plus pi 2 is the identity, the lengths of the projections add up to 1. That is, if b squared is the length of the projection of pi 1, a squared is the length of the projection of pi 2, then a squared plus b squared is the length of the vector phi. And because my quantum system is always unit norm, a squared plus b squared is 1. Okay, so keep this in mind. So when pi 1 plus pi 2 is I, the length squares of the projections add to 1. Okay, this is something that we will use as we go along, but I'm just trying to get you accustomed with the objects in our universe and some of the identities which we will use kind of later on. Okay, so I've told you everything pretty much about the first axiom. So the first axiom tells you where we live, how is a quantum system described, and what are the objects in our universe. Okay, so I'm telling you now axiom 2. So I get to axiom 2. What does axiom 2 say? Axiom 2 says, how does a closed quantum system evolve? Okay, so suppose you leave a quantum system, so you kind of prepare your electron. Think of an electron as your quantum system. So you prepare spin axis of an electron. So you can orient the spin at the axis of spin of an electron in any direction. So you kind of prepared something and you keep it there. Okay, and it's completely, suppose you're able to isolate it from the entire universe. Then how does it evolve, right? So when you prepare it, it has a particular vector representation because it's a quantum system. And then it gets morphed into a different vector, right? How are these two vectors related? That's what axiom 2 says. So the evolution of a closed, isolated quantum system is through a unitary transformation. Okay, so now you understand why I told you about a unitary transformation. What is a unitary transformation? It just preserves length. So if xt2 is the state of a system at time 2 and xt1 is the state of the system at time t1, then xt2 is related to xt1 through a unitary transformation. So xt2 is u times xt1. Okay, so that is the axiom 2. Okay, and just as a kind of a sanity check, I mean, not a sanity check, but just if anybody has any questions at any point of time, just, unmute yourself and just ask the question so that, I address it. Okay, so I'll go to the third axiom. And the third axiom is the most important, is a very important axiom, or possibly one of the most important axioms. And it tells you how is our interaction with a quantum system, how is it governed? Okay, what rules govern our interaction with a quantum system? This is extremely important, and I'll tell you why. Because in a bit, right, if you store a bit on a register, you can just read it, you can just read the bit. But a quantum system is what is called a microscopic object. It cannot be, it is very benign. So even a benign stare at it will modify it. Okay, so you cannot eyeball a quantum state. Just as you eyeball or you read out a classical register, you cannot eyeball a qubit. Okay, your only interaction with a quantum system is through what is called a measurement. And axiom 3 tells you the rules of this measurement, rules of this interaction with a quantum system. So kind of be alert and try to understand this measurement axiom. So I'll describe the measurement axiom. It sounds very weird, but I'll explain it. I'll kind of tear it apart and explain it to you. So let me first kind of just read the axiom. So a measurement is described through a collection of projectors. Okay, so projection operators. Remember, I talked to you about a projection. So it's a collection of projections acting on the inner product space H, or the Hilbert space H. And the only rule for it to be a measurement is that the sum of the projections should be the identity. So any collection of projection operators that sum to the identity forms a measurement. Okay. Now you might ask, what is this? I mean, you're giving me some projection operators and you're calling it a measurement. What is this? What are all these projections? So I'll kind of explain this to you. So think of a measurement. What is the most simple measurement you can think of? The most simple measurement you can think of is like you're measuring, the length of something, right? If you want to measure something, if you want to measure the length of something, what do? You just take a scale, right? So these operators, these indices alpha 1 to alpha k are like the readings on the scale. Okay, so when you perform a measurement, you're going to get one of these readings. So when you perform a measure, so you prepare a quantum state, and suppose you make a measurement, then you are going to get one of these readings. So you're going to get either alpha 1 or alpha 2 or alpha k. So your alpha 1 to alpha k are like the readings on your scale. And this identity, that it sums to identity, is just telling you that you should get one among the k indices alpha 1 to alpha k. So I'll kind of explain this a little bit more detail. So let's kind of get rid of the notation. So I'm instead of calling it pi alpha 1, pi alpha 2 to pi alpha k, I'm just going to call it pi 1, pi 2 to pi k. Okay, so now a measurement is essentially pi 1 to pi k. And I will tell you now what happens if I make a measurement on a quantum state phi. Okay, so suppose you make a measurement pi 1 to pi k. So I told you a measurement is described through the operators pi 1 to pi k that sum to identity. So when you make a measure, so you prepare a quantum system in the state phi, and suppose you make a measurement pi 1 to pi k, what happens? So three things happen, and I'll tell you the three things. First thing, your outcome is random. Okay, you'll have to kind of gulp this feeling. The outcome of your measurement is random, and the probability that you get the outcome k is equal to the length squared of the projection pi k. So take the projection pi k phi. Remember that you had that axis and you projected it, and you will get the projections a squared or b squared. The probability that you will get the outcome k is the length square of pi k phi. Okay. So now you can do a little bit of, remember that if my projection sum to identity, then the sum of the length squared sum to 1. So now you know that the probability of the sum of the sum of the probabilities of the k outcomes is essentially 1, because what you're doing is you're just summing over the length, length squared of all the projections, right? So there'll be just one. So the completeness axiom, which I mentioned here, remember that I said that it should satisfy the completeness axiom. This just translates to the fact that you should get at least one of the k outcomes. Okay. Second thing is that once you make this measurement, the quantum state get collapsed. The quantum state changes. Okay, so the quantum state collapses to one of the following states. So remember, you had prepared the quantum state in the state phi, and you make a measurement. The quantum state will collapse or will change after the measurement, and it will change to one of these states. If you wonder what this denominator is, the denominator is just the length of the projection. So what is happening is that once you make this measurement, the post measurement quantum state is essentially the projection of the state in one among these bases or one among these subspaces in which the projectors project. Third thing is, if you tell me that the outcome is J, then I know what is the post measurement state. Okay, so I know now this might seem a little weird, but I'll try to kind of explain this explain this through a cartoon, and you will kind of understand what's going on. See, remember the classical world. Classical world, if you have a pencil, I just call this the Nataraj pencil, just because there's usually a pencil. So if I have a pencil and I want to measure its length, what do? I just hold a scale to it, right? And what happens? Two things happen. I get the exact measurement of the pencil. There's no uncertainty in it. Second, after I remove the scale, the pencil doesn't change, right? After I make the measurement, the pencil doesn't change, the length of the pencil doesn't change. But this is the classical world. What happens in the quantum world? Suppose you have a quantum pencil, okay, a quantum state. You bring your quantum scale to it, you make a measurement. So two interesting things happen. The outcome is random. So you might have prepared your pencil to be of length 6 centimeter, but when you make the measurement, you're going to get, with some randomness, with some probability, you're going to get a random outcome, and that random outcome could be 2.4 centimeter. And the second thing that happens is the length of the pencil changes post measurement. So this is kind of weird, right? We never observed this in the classical world, but it turns out this is exactly what happens. This is exactly what happens in the quantum world. So outcome is random, and post measurement state, the quantum system itself changes. So if you have if you put all your effort and encoded some information on a quantum state, and you give it to somebody, and that guy tries to read what you have encoded on that quantum state, what he has to do, I told you that all interactions, you cannot stare at the quantum state. You have to make a measurement, but the moment he makes the measurement, whatever you have encoded just changes, right? So it's kind of weird world. So this is kind of the quantum world. So I'll do an example. So I gave you a quantum state in the very beginning, 1 by root 2, 1 by root 2, right? So suppose I make this measurement. So I have two measurement operators, pi minus 0.5 and pi 0.5. So remember, I told you that the indices pi 1 to pi k, the 1 to k, these are the outcomes. So I have two outcomes, either minus 0.5 or plus 0.5. And I have two projections, pi minus 0.5 and pi 0.5. And pi minus 0.5 plus pi 0.5 is identity. It's a completeness. It satisfies the completeness relation. So I have prepared my quantum state in this state. So suppose I make the measurement, then the probability that the outcome I get the outcome minus 0.5 is exactly the length of projection, which is half. So with half probability, I get the outcome minus 0.5. And with half probability, I get the outcome plus 0.5. And if my outcome is minus 0.5, then my state gets collapsed, right? So the state gets collapsed to ket 1. And if I get the outcome 0.5, my state collapses to 0. So remember what has happened. You prepared the state in this state, 1 by root 2, 1 by root 2. That is 1 by root 2 ket 0 plus 1 by root 2 ket 1. And you perform this measurement. the system collapses to either ket 1 or ket 0. Okay, so that's the measurement axiom for you. Okay, so it should tell you one thing, that if I have two states, remember you can't eyeball a state. So if somebody tells you I have prepared a state either ket phi or ket x or ket y, unless ket x and ket y are orthogonal, you can never tell with certainty whether it is ket x or ket y. Okay, so if a guy has prepared a quantum system in either state ket x or ket y, you cannot tell with certainty unless ket x and ket y are orthogonal, because if they're orthogonal, you can project them onto orthogonal subspaces and you can distinguish them, but if not, you cannot do that. Okay, so that is one thing that you have to keep in mind. And to get any, so suppose you do some computation, right? So you encode your information on a quantum state, you do some computation, so your quantum state will evolve. Finally, you want to read out the data, you have to perform a measurement. So if you want to be able to if you want to be able to distinguish your computation result, right, you have to ensure that the different computation results result in different orthogonal states. Otherwise, you can't distinguish. So it might have created a state, but if you cannot distinguish it from the other states, you cannot read the output. Okay, so this is axiom 3 and kind of the things that you have to bear in your mind with respect to axiom 3. So now I'll go to axiom 4. Okay, I will state the axiom and then I will contrast to the classical world so that you can kind of understand the distinction. So in the quantum world, so the axiom 4 talks about the description of a joint quantum system. Remember that I can talk about multiple registers, right? I don't need to talk about just one register. So what is the state of multiple registers? We can talk about it. So axiom 4 talks about the description of a joint quantum system. That is, multiple quantum states are kind of clubbed together. How does it look like? Okay. So suppose quantum system 1 is in state phi 1, quantum system 2 is in state phi 2, and quantum system n is in state phi n, then the state space of the composite quantum system is the tensor product of the Hilbert spaces H1 to Hn. Or if you want, tensor product of the inner product spaces H1 to Hn. So that is the a state space of the constituent joint quantum system. Furthermore, if I have prepared state 1 in phi 1, state 2 in phi 2, and state n in phi n, then the state of the joint system is phi 1 tensor phi 2 all the way tensor phi n. Okay, so you might wonder, what am I saying, right? So I'll contrast it with the classical world for you to get a feel for what I'm saying. So suppose bit 1 is in the bit 1 is in state x1. That is, so the system 1 in the classical world takes the value x1 in a set x1. System 2 takes the value x2 in the state x2. System n takes the value xn in the state xn. Then one can ask, what is the joint system, right? And the joint system is essentially described through its n tuple x1 through xn, taking a value in x1 cross x2 cross xn, right? So this x1 cross x2 cross xn has now transformed into a tensor product h1 to hn, and the n tuple, that is the x1 through xn n tuple, has now transformed into a tensor product phi1 through phi n. Okay, so I'm trying to tell you what is the joint description, the description of a joint quantum state, which is analogous to the description of a multi-bit. Okay, you can think of it as a multi-classical bit. So what is a tensor product? What are the rules that govern it? So I'll kind of just go through that. So if V is an m-dimensional inner product space, W is an n-dimensional inner product space, then V tensor W is an mn dimensional inner product space. Okay, so I'll give you some examples, but I'm just kind of getting you a feel for what's going on. So it's not the direct sum. You might be always thinking of the direct sum. So if you take a vector V, the direct sum of vector V and vector W is essentially append W at the bottom of V. This is not the direct sum. This is the tensor product. So I'll kind of explain. And what is a tensor product space? Essentially, it's the all possible linear combinations of tensor products V tensor W. Okay, so you might ask, what is V tensor W? For the moment, you just think of V tensor W as an ordered pair of vectors. Okay, just think of it as an ordered pair of vectors. I will describe the algebra algebra imposed on this ordered pair of vectors and the linear combination of these ordered pair of vectors. I'm going to describe this. That's what is the tensor product space. Okay, so I'll give you some simple rules. There are three state rules and three operator rules. Very simple. So if it's V1 tensor W plus V2 tensor W, it's essentially that is equal to V1 plus V2 tensor W. So if your second component is the same, you can kind of add the first component. Similarly, if your first component is the same, then how do you add two vectors? So V tensor W1 plus V tensor W2 is V tensor W1 plus W2. You know W1 plus W2 because W1 and W2 are living on a Hilbert space H2 or an inner product space H2. So you can always add them, and you add the second component and you tensor product with the first component. And alpha, so if you take a scalar alpha and you scale the tensor product, you can either associate alpha with U or you can associate alpha with W. Remember, all the inner product spaces are on the same field. The underlying field is either the complex field or the real field. So if alpha is a scalar, you can either associate it with alpha, or you can associate with U, or you can associate with W. Okay, there's a small typo here. It should all be U or it should all be V. My apologies for that. Okay, and in general, so I told you how you can add tensor product vectors when one of the components are the same, but what if the two components are different? So what if I have V1 tensor W plus V2 tensor W2, sorry, V1 tensor W1 plus V2 tensor W2? Well, there is no rule, just keep them apart. Just call them a different object. Okay, so these are the rules governing linear combination in tensor product spaces. Okay, and what is the rules regarding linear transformations? The operators. You know, what is the rules concerning the operator algebra? Well, what operates if A operates on V and B operates on W? Then A tensor B operates on V tensor W. How does it operate? Well, A tensor B, it is A operates on V and B operates W. So this is the first operator distributive law. The second operator distributive law is that if A tensor B operates on a linear combination, then it's essentially A operating on the first component, tensor B operating on the second component, and then you do a linear addition. And A tensor B1 plus B2 is essentially A tensor B1 plus A tensor B2. Okay, so these are the three laws. So why did I do all this? I'm trying to explain how do you describe joint quantum systems and how do they interact, right? That's what I'm trying to do. So I'm telling you what is so remember I told you the universe of objects for the one quantum system. Now I'm telling you the universe of objects in the in a joint quantum system. So how do you talk about operators on the tensor product space, and how do you add them, how do you subtract them, how do you multiply them? These are kind of the rules I'm telling you. The tensor product space. So this is Axiom 4. Okay, and how do you do inner product between so if I have V1 tensor W1 and V2 tensor W2, how do you do inner product between these two vectors? Well, it's V1 inner product V2 times W1 inner product W2. So remember, V1 inner product V2 is already defined in H1. W1 tensor product W2 is defined in H2. So this object on the right is well defined. So that's the inner product between V1 tensor W1 and V2 tensor W2. So I'm kind of telling you all the algebra for the tensor product space. Okay, so I'll do now a concrete example to kind of get you a feel. So a vector V can be 1, 1, 2, but there's not unit norm. Okay, I'm just taking an example. So if I take the vector V 1, 2 and the vector W 3, 4, what is V tensor W? Well, essentially it's the tensor product. So it's each component is multiplied by the entire vector. So 1 times 3, 1 times 4, 2 times 3, 2 times 4. This is the representation for V tensor W. Now, if I take operators A and B, so A is a 2 cross 2 matrix, B is a 2 cross 2 matrix. What is A tensor B? Well, it is a 4 cross 4 matrix, and it's it's kind of a Kronecker product, right? So it's a Kronecker product. So that's exactly what it is. So that's the tensor product. I'll do one simple observation which we will kind of use later on. So if alpha 1 to alpha m is a basis in V, and beta 1 to beta n is a basis in W, furthermore, if it's an orthonormal basis, then an orthonormal basis in V tensor W is alpha I tensor beta j. So you take all ij combinations, and that gives you an orthonormal basis for V tensor W. Okay. So I'll do a simple, kind of a simple observation. All of this leads. So I'm going to, at the end of this talk, I'm going to do just one simple illustration of the power of quantum. And I'm kind of building all the tools towards that through the axioms. So that's kind of the approach. So remember that in C2, ket 0 and ket 1 form an orthonormal basis, right? So from this previous observation, ket 0 tensor ket 0, ket 0 tensor ket 1, ket 1 tensor ket 0, and ket 1 tensor ket 1. This forms an orthonormal basis for HA tensor HB. Okay. I'm going to simplify, in quantum, we always simplify the notation because, remember this, in the classical, what was the comma now has become a tensor, right? A tensor product, right? This O times thing. So the objects in quantum world kind of just keep on, becoming bigger and bigger. So what we do is we shrink that notation by just, so instead of ket 0 tensor ket 1, we write it as ket 0 1. Okay, so ket 0 1 is ket 0 tensor ket 1. So what is an orthonormal basis for C2 tensor C2? Well, it's ket 0 0, comma ket 0 1, comma ket 1 0, comma ket 1 1. Okay, and one can easily show this. So if V1, V2, V3, V4 form an orthonormal basis, then 1 by root 2 V1 plus 1 by root 2 V2, 1 by root 2 V1 minus 1 by root 2 V2, 1 by root 2 V3, this forms an orthonormal basis. So with this very simple thing and the fact that ket 0 0, this forms an orthonormal basis, the vectors at the bottom, which is the 1 by root 2, 1 by root 2 linear combination of ket 0 0, ket 1 1, ket 0 1, ket 1 0, this forms an orthonormal basis. So I'm kind of just setting up some tools for some interesting information processing I will do. Okay, I'm going to tell you about one very important thing now, which is entanglement. Okay, so I'll kind of lead you towards that. Remember, I told you that V tensor W is the space of all linear combinations of little v tensor little w. So take all linear combinations of little v tensor little w. That is your V tensor W space. Okay. I'm going to make one important observation about the space. Okay. It turns out that V tensor W is the span of V tensor little v tensor little w. It is not just these vectors, but it is the span of that. And this has an important consequence. It turns out that some vectors can be written as a tensor product of individual components. That is, if I take this, this BST vector, I can write this BST vector as a vector in U, as a vector in V, tensor a vector in V. So this is so I can write it as ket V tensor ket W, where ket V is this vector and ket W is this vector. But it turns out every vector cannot be written as a pure tensor product. Okay, so to illustrate, so let us take the vector ket 0 0, 1 by root 2 ket 0 0 plus 1 by root 2 ket 1 1. And the statement I want to make is that this cannot be written as a ket 0 plus b ket 1 tensor c ket 0 plus d ket 1. It cannot be written as a pure tensor product of two states. Okay, how do you show this? Well, it's easy to show. Suppose this was true, right? What does this equality say? This equality says that AD equal to 0, because AD is the coefficient of 0, 1 on the left, but the coefficient of 0, 1 on the right is 0. So AD has to be 0. But if you look at the coefficient of 0, 0, it is AC, right? AC 0, 0 is 1 by root 2. So AC is 1 by root 2. So AD equal to 0 and AC equal to 1 by root 2 implies that A cannot be 0. This implies D equal to 0. But if D equal to 0, you can't have BD equal to 1 by root 2. Remember, BD here is on the left-hand side is the inner product between, is the coefficient of ket 1, 1. And the coefficient of ket 1, 1 on the right is 1 by root 2. So you cannot have D equal to 0. But the first identity, the first two relations indicate that D equal to 0, but you cannot have D equal to 0. So there is no, so in other words, there is no choice for A, B, C, and D to ensure that A ket 0 plus B ket 1 tensor C ket 0 plus D ket 1 equal to 1 by root 2 ket 0, 0 plus 1 by root 2 ket 1, 1. So in other words, this vector on the right cannot be written as a pure tensor product of two states, which means that it cannot be written this way. And this has a very important definition in quantum, which I'm going to come to now. So consider a joint quantum system consisting of two constituent quantum systems. Okay, consider a joint quantum system. The joint state vector phi, it lives inside HA tensor HB. We say it is separable if I can write it as phi1 ket tensor phi2. Okay, so ket phi is separable if I can write it as phi1 tensor phi2. If it is not separable, we say it is entangled. Okay, and it turns out this this vector which I showed you is entangled, and this is very important. What it says is that this entangled system doesn't have a component descriptions. That is, you cannot talk about what is its system A description and what is its system B description. See, this is different from the classical world. In the classical world, if you have two classical registers which take the value x1, x2, right? So take two classical registers. You have stored x1 in the first register and x2 in the second register. Then you know what it is. It's the description of the first state is clear. It is x1. You can ask what is the state, what state is the second register in? The answer is x2. You can ask what state is the first register in? You can say x1. But if you take a joint quantum system which is entangled, you cannot write it as phi1 tensor phi2, which means if you ask me what is its first, what is the description of the first component, it doesn't have a description. What is its description as the second state? Second component, it doesn't have a description. That is what is called entangled. So it has a joint description, but the component states don't have any description. That's the notion of entangled. And it turns out this is very important. So all of these are actually entangled states. Okay, so you can whatever argument I gave you before, you can run it on all these states, and these are all entangled states. Now I'm going to do some very interesting information processing with these notions. Okay, with all the notions you have thought, so which I've kind of described so far, I'm going to do some interesting information processing. Okay, so so let's I've taken two Indian cities because I'm actually currently in India, and I had kind of drawn this picture for that. But let's say let's take the I contrast the classical world and the quantum world. Okay, so in the classical world, if x so if you're in say if you're in Krakow and Alice is in Krakow and she holds the register X, and let's say Bob is in Warsaw and he holds the register Y, then each one has a description for his register, right? Alice can say my register is in state X. Bob can say my state is in register Y, is in state Y. But this is not true in the quantum world. In the quantum world, if they hold an entangled state, right? Alice has no description to her component and Bob has no description to his component. Okay, so each qubit has no definite description. So this is very important, and we will do an example to kind of, we'll put all the machinery we studied so far, we kind of went through so far, to do an example of the use of entanglement. Okay, so I'm kind of going through something here quickly. So let's do, I want to do a kind of an example. So let's do an example. Okay, so let's say we have an entangled system shared between Alice and Bob. So Alice is in Krakow, Bob is in Warsaw, and they share an entangled system. And what is that entangled system? That entangled system is this phi plus system. What is phi plus? Phi plus is 1 by root 2 ket 0 0 plus 1 by root 2 ket 1 1. So Alice is holding the first component and Bob is holding the second component. Remember, they don't have their own descriptions, but they are together holding this entangled system. What they'll do, so Alice has one component of the system. So you can think of this as a pair of electrons, with spins, okay? So Alice holds an electron, Bob holds an electron, but the spin of this pair of electrons is described through this through this vector phi plus. Okay, and what Alice does, Alice will do a measurement on her system, on her component of the system. Bob is going to remain silent. Okay, so Alice will perform a measurement. Remember, I told you what is a measurement. A measurement is essentially a collection of projectors that sum to identity. So she will take the projection on the 0 vector and the projection on the 1 vector as the measurement operator. So pi 0 is ket bra 0 0, pi 1 is ket bra 1 1. Remember, I told you that this is read as the ket and this is read as the bra. So I'm reading this as ket bra 0 0. This is ket bra 1 1. If you add ket bra 0 0 and ket bra 1 1, you get the identity. Okay, so Alice performs a measurement, Bob does nothing. Okay, so what is the effective measurement on the joint quantum system? Well, the effective measurement on the joint quantum system is ket bra 0 0 tensor IB, comma ket bra 1 1 tensor IB. Those are the measurement operators on the joint system. Okay, so remember what I told you, that when you perform a measurement, there are three things that happen. The outcome is random, and if you tell me the outcome, I know that the state gets collapsed. Okay, so now we can compute the probabilities of the two outcomes. Okay, it turns out, so you're essentially performing this measurement. So what happens when you perform this measurement? What is happening? So you're performing this measurement on this quantum system phi plus, right? As I told you, I just compactified this notation. So it's 0 0 1 by root 2 0 0 plus 1 by root 2 1 1. When you perform this measurement, you're going to get a random outcome, right? And remember, Alice performs the measurement, Bob is remaining silent. Okay, so Alice gets an outcome. So she gets the outcome 0 with probability half. If she gets the outcome 0, what happens is the system collapses to ket bra 0 0. If she gets the outcome 1, the system collapses to 1 1. So outcome 0 occurs with probability half, and the state collapses to ket 0 0. If the outcome is 1, that happens with probability half, the state collapses to ket 1 1. Okay, so when Alice performs this measurement, you can get one of two outcomes, either 0 or 1. If she gets 0, the state has collapsed to ket 0 0. If she gets 1, the state has collapsed to 1 1. Okay, but remember what happens? It's random, right? So with probability half, she gets 0. With probability half, she gets 1. But remember what has happened. The state of the system has collapsed, right? So now if Bob performs a measurement, so Alice performs her measurement and she just kind of, she holds her outcome. But what has happened is the system has collapsed. Now, if Bob performs a measurement, he will get exactly the same outcome as Alice. So if Alice has got 0, Bob will get 0. If Alice gets 1, Bob gets 1. So in other words, with probability half, both of them get 0 or both of them get 1. So which means that these are like, these are like secret keys that are just randomly generated, distributedly. Remember I told you Alice is in Krakow and Bob is in Warsaw. They have this entangled pair. Alice just performs a measurement. She gets a random outcome. And the moment she gets the random outcome, she knows Bob will get exactly the same outcome. Because when he performs this measurement, he will get, because the state has collapsed. So once she's performed this measurement, Bob's state has also collapsed. So now when he performs the measurement, the outcome is deterministic. So this is very interesting because essentially you are generating keys, random keys that are random but are strongly correlated. So if they want to do some communication with some secrecy, they can use these keys that are generated from this entangled pair for performing encryption. So today we spend a lot of effort to have secret random keys at distributed locations. But if we can actually harness the power of this entangled state, you can actually generate random distributed keys that are strongly correlated. And we don't have to, all the cryptographic primitives that we use to generate these keys kind of go unwanted. So it's rather much easier to generate these keys. Okay, so this is kind of the utility of quantum states. Essentially, I've given you only one utility of quantum states, which is you can harness entanglement to generate random keys that are random private keys. I mean, these are essentially private keys for cryptographic communication across distributed parties and distributed states. All that you need is that you should be able to separate components of an entangled pair across two terminals. And it turns out that people have actually separated components of an entangled quantum system as far as like 1,000 kilometers apart. So you can indeed separate components of an entangled pair far across. So in other words, what we have kind of covered so far is we have covered all the axioms of quantum mechanics, and I've kind of demonstrated how the notions of measurement and tensor product and entanglement can lead to new information processing strategies. And here I'm essentially able to extract public keys distributedly at two terminals. So with this, I want to kind of take a stock of with how much time I have. But if we don't have much time, this is a good point to kind of pause.
I suggest, Arun, that we ask some questions. You will have another hour next week. By the way, the talk is great. You should write a book about this.
Okay. Thank you. But yeah, I want to keep it
when we see each other. Okay, guys, any questions to Arun? Don't be shy.
Yeah, please, please ask whatever you have, and we can kind of.
I'm sure Abraham has a question. He's still there, quiet.
So I have one question, if I may.
Yeah, please.
So you started with saying that a quantum space is it can be infinite dimensional Hilbert space. So I just wonder how large is an intersection of this field with classical functional analysis and operator theory, and if it's I don't know, broadly used, or it's something completely different.
No, can you please repeat your question once again? I kind of got, but I want to, kind of, yeah.
Yeah, so I'm asking because you started by saying that one can consider all this stuff in Hilbert space, which is infinite dimensional in inner product space. So I wonder if How large is intersection of these studies with classical functional analysis and operator theory
Oh, okay.
in Hilbert spaces?
Yeah. Yeah. See, I think the key point that one needs to know from classical functional analysis and all of that is the conditions for boundedness of operators. Okay. So that is really the key. Really, if you're kind of an expert in functional analysis, what you essentially need to know is the conditions for boundedness of operators, and when you can, what conditions you need for your operators to be bounded, what kind of measurements to design. But really, the intersection between that and functional analysis is not too much. You just need to know the conditions for boundedness, conditions of exchange of some operators, but otherwise, all of the ideas are essentially understood in the finite dimensional case, though some technicalities you have to learn in the infinite dimensional case. Yeah, it's like this. You don't really need to know if you ask me, if you're working in some information processing, how much of measure theory do you need? Well, you really need to know so much measure theory to be able to tell when you can exchange limits and integrals, right? So that's pretty much what it is. Does that answer your question?
Yeah, I think so.
Yeah.
Another question.
Also, maybe I should mention that there are two very good books. One is Nielsen and Chuang. It's a good book, though it's a slightly verbose book. You can also look at Wild, Mark Wild's book on quantum information theory. So you can just read the first two, chapter 3 and chapter 4, to kind of just get the basics. Yeah, again, you'll have to kind of make these pictures on your own, but these are two good books. There's also one good Italian book. If somebody's interested, you can send me an email. I'll send the authors. I haven't read it myself, but kind of just look through it. I'll be happy to answer any questions.
So maybe one more.
Yeah,
there was
please.
this part with unitary transformation, and you said that a difference between what happens in state T1 and T2 is a unitary transformation, but it depends on a difference of times, right? It's a different transformation for each difference, or is the one fixed transformation?
No, so any evolution of a closed quantum system can be described through a specific unitary transformation. So, in other words, if you have observed a closed quantum system evolve, that evolution can be described through some unitary transformation. It's not one unitary transformation always, but every evolution is associated with a unitary transformation.
But by evolution, you mean 2 points in time, and what's between, right? Okay.
Yes, 2 points in time without any external interaction, without any external energy being added. Or any external interaction. So it's a closed, isolated quantum system. Evolution means it's a time evolution. So yeah, it's time evolution.
Okay, thanks.
Sure.
Okay, I think I lost connection. Arun, are you there?
Yeah, I'm there. And there was one more question. Yeah,
Okay.
I just answered that.
Okay, I lost my wireless, but recover.
Don't hesitate. You can ask me any question. Even if you want some references, you can ask me, and I'll be happy to tell. There are quite a few tutorials on the internet, and it's good to go through them. Yeah, we thought that it's a good idea to give this presentation first before start talking about research results, because later Mohsen is going to be talking also about some of his results. And I'm guessing this video will be saved, right, Brent?
Yes, that's correct. Yeah, we'll have it up on the website probably later this week.
Yeah. So anybody can watch, and if you have any questions, feel free. You can also ask me next week.
Okay, so I understand all the questions were asked, and we are done.
Yeah.
Yes. Thank you,
Yes.
Arun, for joining us from
Sure.
India. And next week,
Sure.
it's probably the same. Connection was good. My collapse, not yours. Yeah.
Thanks, Arun.
We are
Thank you
developing
very
fast.
much. Thank you.
Thanks, everybody.
Bye.
Thank you.
Bye.
See you then. Bye. Thank you.
Thank you.
Thank you.